Okay, so we explained the central limit theorem and the t-distribution and how these are useful in practice. Now we're going to show an example from genomics. So this example is based on real data. It's an experiment that was performed on 2 strains of mice. It's a gene expression experiment. This was actually done with microarrays, but what we're talking about today is actually independent of platform. You know, the data for RNA-seq would look similar. So what was done for this experiment? Well, we had 12 mice of each strain. That's our sample. Our population would be all the mice from the first strain and all the mice from the other strain that exist in the world. And they have, so for each gene, there is some population average that would be like the population mean that we talked about in the previous module. But now we have 12 and 12. Now, one of the things that we did in this experiment is we took RNA from each one of these mice and we saved it. We also created a pool of all that RNA for each strain. So now we have 2 pools, one from strain 1, one from strain 2. And then we created 4 what we call technical replicates. So it's the same RNA divided in 4. So that's going to give us, we're going to get measurements for those 4 and 4 samples. But that variability that we see for those data is technical variability. It's the variability that comes from the technology. We're later going to show both the variability you get from the technical replicates and from the biological replicates. So if we do it like this, if we take this pool and we then create 4 replicates, now the population is different. Think about what the population is. The population here would be this sample, this particular sample that we have here. We're sampling from there. We're sampling 4 subsamples from that one. So any inference, any statistical inference we perform is going to be about that very specific sample, not about the population of mice of this strain. So let's look at some data from this experiment. So here are 2 genes. We had 4 samples, so we get 4 measurements for each one. And you can see the 4 green points and the 4 orange points. Those are the measurements. Now, if we compute a t-statistic here, assuming that gene expression is normally distributed in the log scale, then we're safe using the t-statistic, and we would get a very, very small p-value telling us that this gene is differentially expressed between the 2 strains. Right? Same for gene 2. Very, very small variability within the groups, very large variability between the groups. The t-statistic is humongous. The probability of seeing something that big under the null is minuscule. In the code that we put up on the web, you can run that code and you can actually get the actual p-values for these numbers, for these data. So now, what happens if instead of these 4 technical replicates, we consider the 12, what I'm going to call biological replicates, the 12 individuals. So in this plot, these are box plots. And the box plots contain information for all the genes on the microarray. And what I did is for each gene, I computed the standard deviation across the 4 technical replicates. I picked one of the 2 strains. So now I have one of these for each gene. And then I did the same thing for the 12 individual mice. And that's on the right side box plot. So immediately we notice that the variability in the biological replicates is much bigger. And that should not surprise us. Microarray technology is quite precise. When you give it 2 identical RNA samples, you get very similar answers. However, the biological replicates include natural variability. This is not just technical. Now we're seeing variability from individual to individual for every gene. That has nothing to do with technology. It's nature. So that is the variability that we want to measure if we want to perform statistical inference on the strains. So now here are those same 2 genes that we saw earlier that were showing very clear differences between the two pooled samples. And now we see a very different story. For gene 1, we still see that there's a difference in the mean, but now we have all this variability within each group. For the second gene, that within group variability is not as large. If you compute a t-statistic here, it's not significant. If you compute a t-statistic here, it is significant. So what changed? What changed is that this gene has a lot of within group natural variability. Just that the population standard deviation is large. We don't see that when we look at technical replicates. We are looking at the same RNA over and over again, as opposed to RNA from different individuals. So this is an important distinction to make. Now we're making inference about the strains as a population. Say that one of your colleagues is going to try to reproduce your results, and they're going to take another sample of another 12 mice. If they do that, they're going to see this variability. And of course, if we were to guess which of these two genes would be more likely to reproduce as differentially expressed, you would have to go with the one on the right. And statistical inference helps us determine that. So in the next modules, we're going to show you what to do when you have high throughput data. We have high throughput data. Now we have a t-test for each gene. And how do we decide which genes to report, which genes we think are statistically significant?